What if everything we've been told about protecting muscle after 75 is only half the story? Most people believe the answer is simple. Eat more meat, get more protein, and muscle loss will slow down. But here's the uncomfortable truth doctors are beginning to discuss. After 75, the body often stops using protein efficiently. You can eat the same steak you ate 20 years ago, and your muscles may barely respond. Now here's the surprising part. Researchers are looking at a forgotten fruit that may actually help aging muscles respond better to nutrients, in some ways protecting muscle cells more effectively than meat alone. And almost nobody over 75 is talking about it. Welcome back to my brand new video. For most of our lives, we are taught a simple rule about muscle. Eat enough protein and the body will maintain strength. In youth and middle age, this assumption is largely correct. When protein enters the body, it is broken down into amino acids, which circulate through the bloodstream and signal muscle cells to begin repair and growth. The process is efficient. Muscles receive the signal, absorb the amino acids, and rebuild the microscopic fibers that allow us to lift, walk, and maintain stability. But after the age of 75, something subtle yet profound begins to change inside the body. Doctors and researchers increasingly describe this change through a biological phenomenon known as anabolic resistance. Anabolic resistance means the muscles gradually become less sensitive to the signals that normally stimulate repair and growth. The same amount of protein that once triggered strong muscle rebuilding now produces a weaker response. It is not that protein stops working completely, but the efficiency of the system declines. Muscle cells require stronger stimulation, more supportive conditions, and a healthier internal environment to respond in the same way they once did decades earlier. This shift occurs for several biological reasons. Aging muscle cells experience changes in their signaling pathways, particularly those responsible for detecting amino acids and activating protein synthesis. These pathways are influenced by hormones, inflammatory molecules, and the overall metabolic state of the body. With advancing age, hormonal signals, such as growth hormone and testosterone decline, while inflammatory markers slowly rise. This combination creates an environment where muscle cells become hesitant, almost resistant, to the rebuilding process. The digestive system also changes. Stomach acid production often decreases with age, which can make protein digestion less efficient. If protein is not broken down properly into its component amino acids, fewer building blocks enter the bloodstream. Even when an older adult eats the same portion of meat they did years earlier, the body may extract fewer usable nutrients from that meal. The muscles are therefore receiving a weaker signal and fewer materials for repair. Blood circulation adds another layer to this problem. Muscles rely on healthy blood vessels to deliver amino acids, oxygen, and hormones. As arteries gradually lose elasticity with age, nutrient delivery becomes less efficient. The result is that even when nutrients are present in the bloodstream, they may not reach muscle tissue as effectively as before. Scientists studying aging physiology have observed that this resistance creates a dangerous cycle. As muscles become less responsive to protein, muscle mass slowly declines. With less muscle mass, metabolism slows, and physical activity often decreases. Reduced movement then further weakens the signaling pathways that stimulate muscle repair. Over time, this cycle contributes to the condition physicians refer to as sarcopenia, the progressive loss of muscle associated with aging. What makes anabolic resistance particularly challenging is that it often develops quietly. An individual may continue eating similar foods, maintaining familiar routines, and yet notice a gradual decline in strength. Standing from a chair becomes slightly harder. Walking longer distances requires more effort. Recovery after minor physical activity takes longer. These small signals are the body's way of revealing that the internal machinery responsible for muscle maintenance is becoming less responsive to the nutritional signals it once easily understood. If anabolic resistance weakens the muscle's response to protein, chronic inflammation quietly intensifies the problem. Many people imagine inflammation as something dramatic, swelling, redness, or pain after an injury. But the kind that influences aging muscles is different. It is subtle, persistent, and often invisible. Scientists describe this slow-burning biological state as chronic inflammation. Unlike the short-term inflammation that helps the body heal wounds, this form lingers in the background of the bloodstream for years, quietly interfering with the body's repair systems. After the age of 75, the immune system begins to behave differently. Instead of responding sharply to threats and then calming down, it often remains slightly activated. Immune cells release inflammatory molecules, known as cytokines, at low but constant levels. These molecules circulate through the body and interact with tissues, including muscle fibers. Over time, they disrupt the delicate signaling pathways that muscles rely on to repair and maintain themselves. Muscle tissue is not simply a mechanical structure. It is biologically active and constantly renewing itself. Every day, microscopic damage occurs within muscle fibers as we move, walk, or perform simple tasks. Under normal conditions, the body repairs this damage quickly through a process known as muscle protein synthesis. This process rebuilds and strengthens the fibers, maintaining muscle mass and function. However, inflammatory molecules interfere with the signals that initiate this repair process. One of the key effects of chronic inflammation is that it shifts the body's balance from rebuilding tissue toward breaking it down. Instead of encouraging muscle protein synthesis, inflammatory signals stimulate pathways that promote protein degradation. The body begins dismantling muscle proteins faster than it rebuilds them. This imbalance gradually reduces muscle size and strength. Even if a person continues eating adequate protein, oxidative stress adds another layer to this process. As inflammatory activity increases, the body produces more unstable molecules known as free radicals. These molecules damage cellular structures, including the membranes and mitochondria inside muscle cells. Over time, this damage reduces the efficiency of muscle fibers and makes them more vulnerable to decline. Scientists describe this combined state of inflammation and oxidative stress as inflammaging, a biological condition strongly associated with aging. Another consequence of chronic inflammation is reduced communication between muscles and the rest of the body. Muscles rely on hormonal signals, nutrient availability, and nervous system input to function properly. Inflammatory molecules disrupt this communication network. Insulin sensitivity may decline, making it harder for muscle cells to absorb glucose for energy. Blood vessel function may weaken, reducing the delivery of oxygen and nutrients. The muscle cell, in essence, begins operating in a hostile internal environment. This is why muscle loss after 75 is rarely the result of a single factor. It is not simply about eating less protein or exercising less frequently. The deeper issue lies in the biological environment surrounding the muscle. When inflammation quietly dominates that environment, the body's repair systems struggle to function efficiently. Over time, the cumulative effect becomes visible in daily life. Strength diminishes gradually. Physical tasks require more effort. Recovery from activity slows. The muscle fibers themselves are still present, but the conditions required to maintain them are no longer stable. The body's internal chemistry begins favoring breakdown over renewal, subtly reshaping the balance that once protected muscle throughout earlier decades of life. When we think about muscle strength, most people imagine size. Larger muscles must mean stronger muscles. But inside every muscle fiber exists a far more important factor that determines how well that muscle actually performs. Deep within the cell are tiny structures responsible for energy production. These microscopic engines are known as mitochondria. They are responsible for converting oxygen and nutrients into usable cellular energy, the fuel that allows muscle fibers to contract, sustain movement, and recover after activity. In youth, these cellular engines function with remarkable efficiency. Every step you take, every time you stand from a chair or climb stairs, thousands of mitochondria inside each muscle fiber produce a steady supply of energy. They work silently, continuously converting nutrients into a molecule called adenosine triphosphate, often abbreviated as ADP. ADP is the immediate energy currency of the body. Without it, muscles cannot contract, nerves cannot send signals, and cells cannot repair themselves. But as the body ages, these energy-producing structures begin to decline in both number and efficiency. This decline becomes particularly noticeable after the age of 75. The muscle fibers themselves may still exist, but their internal power supply weakens. When mitochondria become less efficient, the muscle simply cannot generate energy at the same rate it once did. This change explains something many older adults experience, but rarely understand. The issue is not always that the muscle is gone. Often the muscle is still present, but it tires quickly. Tasks that once felt effortless suddenly require more effort. Walking longer distances becomes exhausting. Standing for extended periods leads to fatigue in the legs. These changes are not purely about strength. They are about energy production within the muscle cells. Scientists studying aging muscles have observed that mitochondrial decline reduces endurance far earlier than it reduces muscle size. In other words, a person may still appear physically capable, yet internally their muscle cells are struggling to generate the energy required for sustained activity. When energy production slows, recovery also becomes slower. After mild exertion, muscles require more time to restore their energy reserves and repair microscopic damage. Another factor complicates this process. Aging mitochondria produce more unstable molecules, known as free radicals. These molecules contribute to oxidative stress, damaging nearby cellular structures, including proteins, membranes, and even the mitochondria themselves. Over time, this creates a feedback loop. Damaged mitochondria produce more oxidative stress, which in turn damages additional mitochondria, gradually weakening the muscle's internal energy system. Circulation also plays a critical role in this process. Mitochondria rely on oxygen delivered through the bloodstream. When blood flow decreases due to aging arteries, less oxygen reaches the muscle cells. Without adequate oxygen, mitochondria cannot produce ATP efficiently. The muscle then shifts toward less efficient metabolic pathways, producing energy more slowly and creating fatigue more quickly. This is why muscle endurance often declines faster than muscle mass itself. The structure of the muscle remains, but its internal power plants are operating below capacity. Strength becomes unpredictable. One moment a person feels stable and capable, and the next moment their muscles feel drained of energy. Understanding this biological shift changes how we think about aging muscles. Protecting muscle is not simply about preserving size or increasing protein intake. It also involves maintaining the health of the mitochondria inside those muscle fibers. When these microscopic engines remain functional, muscles retain the ability to generate energy, sustain movement, and recover after activity. If you find this kind of health science valuable and want more evidence-based discussions about aging, longevity, and protecting your body after 60 or 70, take a moment to share this video with someone who might benefit from it. And if you haven't already, subscribe to my YouTube channel Senior Ageless for more insights into how the human body continues adapting and responding to the choices we make every day as time moves forward through the quiet biology of aging muscle and the cellular energy systems that keep it alive. Muscle preservation in later life depends on more than nutrition and cellular signaling. Even when the body receives adequate nutrients, those nutrients must physically reach the muscle tissue. This is where circulation becomes critically important. Blood vessels act as the transportation network of the body, carrying oxygen, hormones, and amino acids to the muscles that depend on them for survival. Without efficient circulation, the entire process of muscle maintenance begins to weaken. Scientists often describe the inner lining of blood vessels as the endothelium, a thin but highly active cellular layer that controls how blood flows through the vascular system. In younger adults, the endothelium remains flexible and responsive. Blood vessels expand easily when muscles demand more oxygen and nutrients during movement. This expansion is partly controlled by a signaling molecule called nitric oxide. Nitric oxide relaxes the smooth muscles surrounding blood vessels, allowing them to widen so that more blood can pass through. When muscles contract during walking, lifting, or even standing, nitric oxide helps increase circulation exactly where it is needed. As the body ages, however, the efficiency of this system gradually declines. The endothelial cells lining the arteries become less responsive, and the production of nitric oxide decreases. Arteries slowly stiffen, losing the elasticity that once allowed them to expand and contract with ease. This condition is often associated with endothelial dysfunction, a process closely linked with aging and cardiovascular changes. When blood vessels lose their flexibility, the consequences extend far beyond the heart. Muscles rely heavily on circulation to receive the materials required for repair and maintenance. Amino acids from dietary protein travel through the bloodstream before reaching muscle cells. Oxygen carried by red blood cells fuels mitochondrial energy production. Hormones that stimulate muscle repair also move through the vascular system. When circulation becomes restricted, these essential components arrive more slowly and in smaller quantities. The muscle cell itself does not have direct control over this delivery system. It must rely entirely on the efficiency of nearby blood vessels. If those vessels cannot expand adequately, the muscle receives a reduced supply of oxygen and nutrients. Even if a person consumes sufficient protein
At the
and
heart of every
maintains
muscle
physical
cell,
activity,
mitochondria act
effectiveness
like
of
power
those efforts
plants,
may be
converting
limited
nutrients
by
into
impaired
ATP,
circulation.
the body's
This
energy
is one
currency.
reason why older
This ATP
adults
fuels
often
muscle
experience slower
contractions,
recovery
giving you the
after
strength and
physical
power
exertion.
through any
After
challenge.
muscles perform work, they require increased blood flow to deliver nutrients for repair and remove metabolic byproducts produced during activity. When circulation is reduced, this recovery process becomes delayed. Muscles remain fatigued for longer periods, and the rebuilding process becomes less efficient. Another important aspect of circulation is the removal of waste products from muscle metabolism. During physical activity, muscle cells produce compounds such as lactic acid and other metabolic byproducts. Efficient blood flow helps transport these substances away from the muscle, preventing accumulation that contributes to fatigue and discomfort. Reduced circulation allows these compounds to linger longer within the tissue, further slowing recovery. Over time, the combined effects of reduced nutrient delivery, lower oxygen availability, and slower waste removal create an environment in which muscle preservation becomes increasingly difficult. The muscle fibers may still be structurally intact, but the support systems required to maintain their strength and function are gradually weakening. This reveals a deeper truth about the human body. Muscles are not isolated structures working independently. They are part of an interconnected biological system in which circulation acts as the lifeline that sustains every cell. When that lifeline becomes restricted, the muscle's ability to repair, maintain energy production, and respond to nutrients begins to diminish through the quiet but powerful influence of vascular aging and the gradual loss of flexibility within the body circulatory network. If there is one lesson that science continues to reveal about aging, it is that longevity and muscle preservation are never about a single nutrient, a single food, or a single habit. The human body is not a simple machine where one input produces a guaranteed output. It is a complex network of interconnected systems, each influencing the other in ways that are often invisible but profoundly significant. After 75, this interconnection becomes even more critical. Muscle survival is not simply a matter of eating more meat or increasing protein intake. It is about creating an environment inside the body where the cells responsible for repair, growth, and energy production can function optimally. This is where certain overlooked foods, particularly pomegranate, begin to show remarkable potential. Unlike meat, which primarily provides amino acids for protein synthesis, the bioactive compounds in pomegranate act on multiple systems simultaneously. Polyphenol and antioxidants found in the fruit reduce chronic inflammation, a condition that subtly accelerates muscle breakdown. By calming this low-grade inflammatory activity, pomegranate allows muscle cells to respond more effectively to the protein already present in the diet. In a sense, it prepares the terrain, making the environment more favorable for the body's natural repair mechanisms to operate efficiently. Pomegranate also supports mitochondrial health, the energy engines of each muscle cell. After 75, these engines often lose efficiency, leaving muscles tired even if they are structurally intact. Compounds in pomegranate help protect mitochondria from oxidative stress and enhance their function, meaning muscles can generate more energy from the nutrients they receive. This is not just about endurance. It is about maintaining the very capacity of the cell to act, repair, and respond to daily physical activity. Circulation is another critical factor influenced by this fruit. Healthy blood flow ensures that nutrients, oxygen, and hormones reach muscle tissue where they are needed. Pomegranate has been shown to improve endothelial function and increase nitric oxide availability, allowing blood vessels to remain flexible and responsive. In practical terms, this means that every meal, every walk, Every small movement has a greater chance of stimulating muscle repair and maintaining strength. The fiber in pomegranate adds yet another layer of benefit. Gut health is intimately connected with muscle health, particularly in older adults. A healthy gut microbiome improves nutrient absorption and reduces systemic inflammation. The fruit feeds beneficial bacteria, supporting a chain reaction where improved digestion leads to better nutrient delivery and, ultimately, stronger muscle response. The broader lesson is that muscle preservation after 75 requires synergy. Meat provides amino acids, but amino acids alone cannot overcome inflammation, poor circulation, mitochondrial decline, or digestive inefficiency. Pomegranate works on multiple fronts, enhancing the environment in which muscles live. By combining nutrient intake with support for cellular function, blood flow, and gut health, older adults can preserve strength and energy far more effectively than relying on protein alone. If you find this insight valuable and want to see more ways to protect your strength and vitality as you age, take a moment to share this video with someone who would benefit from it. Don't forget to subscribe to my YouTube channel Senior Ageless for more evidence-based guidance, and follow for more videos that explore the science behind healthy, resilient aging. This approach is not about shortcuts or magic solutions. It is about understanding the subtle, interconnected systems that make muscle preservation and longevity possible, and giving your body the support it truly needs through intelligent, science-backed choices.